Cedric Villani is really a person with two separate personalities and hats. He's one of the great mathematicians of our time. He got his degree from the École Normale in Paris in 1996, doctorate 2 years later, and soon became a professor at the École Normale. He won the prize of the European Mathematical Society in 2008, the Fermat Prize in 2009, and the Fields Medal, which is in many ways still the premier prize in mathematics, in 2010, the last cycle. He's the director of the Institut Poincaré in Paris, sort of parallel institution to this one, and therefore one of the few people who understands what my life is like. But this, in addition to this very high-profile, high-powered research in mathematics, he has a persona in public understanding of mathematics. He's written many popular books and articles on optimal transport and on other things. Perhaps the most spectacular of these is Théorème Vivant, Theorem Alive, or Living Theorem, which will be translated into English next year. It's caused quite a stir in Paris, translated already into German. I don't know why they're first, but...
They were too efficient.
Ah, there you are.
Translation needs time and taking the long way, you know.
I often think that mathematics lectures, even great ones like this, we have a wonderful audience here, perhaps 120 people, but football gets 30,000 people, 50,000 people. Well, Cedric has had 100,000 views on YouTube for his TED Talk, so we're in the running. We're in the running. Cedric, without further ado.
And soon 100,000 views on that alternative media that was well described by Will. Okay. So, welcome everybody. It's a pleasure to be here. It will be a public lecture, so this is a mathematics lecture intended for non-specialists. And specialists will forgive me if I sometimes say things that are not quite true, but almost. Yes, I see that Craig here on the first row may be a bit tough, but will do nevertheless. This is, however, even though it's for lay audience, it will bear on the same subject that has been the main topic in one of the 2 semesters that were held here this fall. So it will be a topic of optimal transport, and the same things that I will talk about were the ones the subjects that we considered in particular in my working seminar with the students and postdocs here. The conference, this lecture is entitled Triangles, Gas, Prices and Men, so one can expect that there will be quite a range of topics covered. We'll go through this one after the other calmly. And we'll start with a few reflections about the nature of mathematics. Sometimes it's not easy to explain what we do as mathematicians and what is the relation to real life, as people say. One can debate whether there is a real life or not, but the connection of mathematics to the world, I think there's a very good literary image that can be used for that, and which is illustrated here. So this is an illustration of the Lady of Shalott. This is a poem by Arthur Lord Tennyson in describing a legend from the Arthurian times in which there is this lady, princess or something, who is in some kind of castle and has been struck by a curse. And the curse is that she is unable to look at the world directly. Only through the reflection of a mirror is she allowed to look at the world. The story is beautiful and tragic because one day arrives Sir Lancelot that we see here in the mirror, and he's so handsome that she has to look at him directly, and then the curse is accomplished, she dies, etc. It's very tragic. But it's a poem that has been the occasion of many comments and many attempts of explanations to know whether there was something particular in the mind of Tennyson when he wrote it. And because, you know, in poetry, when you don't explain, everybody is entitled to give his own interpretation or her own interpretation. I like to think that this is an allegory of the mathematician. Struck by some curse, is always contemplating the real world but unable to look at it directly. Only through the reflection of abstraction is he allowed to do so, or is she allowed to do so. And this reflection will take the form of formulas. This can be, for instance, as you see here below, the contrast is not, I should have used a different color than black and blue. Whatever, this is the incompressible Euler equation. The particular form of the equation, never mind. I write it for you just because it's beautiful, these kind of mathematical symbols. And the important is that this equation is describing something quite real that can be the river, as we see through the window of the picture here, the Lady of Shalott. In the tale, in the end, her body goes along the river and arrives near Lancelot, and he says, "Who is this fair lady?" and so on. So that particular river, you can think of it as something very sensitive that you can feel with your hand and so on. But you can also think about it as something that is described by these kind of equations. And when you are a mathematician, that is the way you look at the river. This model or another model or a different model always will be the abstract reflections of the real life, so to speak, as are all the other mathematical phenomena and formula which I represented here. By the way, the one on the top right, the Einstein equations of general relativity, was the main subject of the other semester in this MSRI fall meetings that were organized in parallel to our seminar on optimal transport, our program on optimal transport. So that is for nature of mathematics, so to speak. Now, there is a life in the real world that is studied through mathematics, but then the mathematical reflection kind of comes alive, as also happens in some movies and some animated cartoons. And these objects, mathematical objects, do have their own life and adventures, and sometimes they are studied for their own sake. And it's a picture and a field that is moving a lot and very, very much in progress, contrary to a popular belief. For instance, the rate of production, if I may say, of new theorems and new mathematical ideas is higher today as it ever was before. And we know nowadays maybe hundreds of thousands theorems are proven every year. And in particular, it means that the mathematics of today is very different from mathematics of 1800. It means that there are also many problems, many countries in this abstract world which have still not been explored or only hardly explored. There are open problems, some mysteries, so to speak. And some are very famous, some are not, some become famous, some you think are just anecdotal and they become very important one day, and so forth. If you ask a mathematician what is the most famous problem of all, maybe he will answer Riemann hypothesis. There's a good chance. Hilbert himself used to say this is absolutely the most important problem in mathematics nowadays. That was in his time, and still today we haven't made so much progress from what he was able to know. So Riemann hypothesis, it was your opportunity to speak of the personality and life of Riemann, one of the most remarkable mathematicians that ever was, one of the most remarkable men in our history. Among other things, Riemann found this hypothesis. I will not describe it very precisely, but it's about a certain function whose formula you find here at the bottom of my slide. The zeta function is the sum of the inverse of the power s of the natural integers. Anyway, it's a function of a complex parameter s, so you can imagine it as a function defined on a plane, and the problem is to know where this function achieves the value 0. Some of these places are well known, others are not well known, and Riemann, for various reasons, thought that all the places where it was not well known, all the zeros that were not well identified, will all line on a single line, a vertical line in the plane. And, you know, it's a function, we can compute it. Nowadays, you can compute it using computers and so on. Riemann did some computations with his hand and so on. Now we can use the computer and check whether it looks true or not. And it was checked that the intuition of Riemann really seems right. It has been checked for billions and billions of zeros. Billions and billions of times, whenever we have a new zero of this function, it is on this line, real part equals 1/2, that Riemann had predicted. And you see, this is one of the things that maybe illustrates most the particularity of mathematics among other sciences. Even though mathematics is a science, like other sciences, it is a particular science because in any science, if some assumption you check 1,000,000 times, if it is always satisfied, you will assume it is true. In any fields of our lives, actually, in any fields of the knowledge of mankind, something with some assumption which is checked millions of times and never found to be false, you will get it for granted that it is true. But not in mathematics. Even though the assumption has been checked billions of times, we are still not convinced. We need a proof that is absolutely rigorous so that there is not the faintest possibility, being 1 over billions of billions of billions, that it is not true. Now, what is this assumption good for? The second formula here relates the zeta function to properties of prime numbers. The prime numbers are the elementary numbers like 2, 3, 5, 7, etc., that cannot be divided further as the product of two lower integers. So the zeta function is related through this formula to the prime numbers, and somehow, if Riemann's intuition is correct, it means that in some sense, the prime numbers are distributed kind of randomly among the integers. Randomly and in a way that has certain regularities. And that's also one reason why it's so fascinating. Through this analysis of a function, we can find some understanding of these prime numbers which have been fascinating to mankind for thousands of years. A few years ago, The Guardian fantasized that if this Riemann assumption would be proved or disproved, it could bring disaster to internet. This was at the time when the Riemann assumption was the most famous of the 7 problems that were put to prize by the Clay Mathematics Institute for $1 million each. 7 important problems. One of them was the Poincaré conjecture that was solved later by Gregory Perelman. The other 6 are still unsolved. I tell you, there are many, many easier ways to win $1 million. But anyway, the assumption behind this article by The Guardian we can reconstruct. Because prime numbers have been used so heavily in the coding in internet for secret codes, and because they are related to the Riemann hypothesis, there was this idea that if we solve it, then it will enable people to crack codes by factorizing and so on. Of course, with just a few minutes that I spent on explaining this, you can understand that this is nonsense. One reason being that anyway, if the Riemann assumption has been found to be true billions and billions of times for practical purposes such as coding, we can assume it to be true. And the deeper reason being that if the Riemann hypothesis precisely says that prime numbers are kind of randomly distributed, what the hell will it help you to crack a code? Of course, nothing. But we don't need this. Anyway, it's not in this kind of justification that the Riemann hypothesis finds its importance. It's the fact that it's connected to so many different problems of mathematics, including some pure considerations related to quantum mechanics and spectra of random atoms, in a sense, and the fact that it is so simple, so hard to prove, so central. It has its justification within science, even if it is not of no use for the technology. And mathematicians know that when this is solved and understood, then it will be kind of a revolution in mathematics. Riemann did not only work on these kind of number theoretical problems. In fact, with just a few papers, he did a bit of a revolution in almost every domain in mathematics, in particular geometry. We learn in high school, about the Euclidean geometry with planes and lines and circles and so on, and we have the beautiful elements of Euclid, which remain to this day the most edited treatise in the history of mankind. we learn about all this Euclidean geometry, but one day you want to consider geometry for more general spaces. And it was Riemann who found the set of axioms, the formalism that we use still nowadays to describe non-Euclidean geometry. In the Riemannian world, in the Riemannian geometry, units of length may change from place to place, and things may be short length at some place, longer length at some other. The unit of length are changing from place to place. And of course, we cannot speak of a line any longer, but still it makes sense to speak of the shortest path, even in this curved kind of environment, like the shortest path from here to the, I don't know, to the tables there. It will be some path that is curved, that is not Euclidean geometry, but it still makes sense. And we can study how these paths compare to the usual lines that we are used to in Euclidean geometry. And this was the birth of this important concept named curvature. You know, in mathematics, as Poincaré once said, the problem is not in science in general. You make science with facts, as you make a house with stones and bricks. But a science is no more an accumulation of facts than a house is an accumulation of stones. You need to order things. And curvature is one of the things that enable us to order geometry. In particular, Riemann shows that there is this notion of curvature. If it is positive curvature, meaning that the geodesics tend to get closer to each other than if we were in Euclidean space, or in negative curvature, they tend to be further apart than if we were in Euclidean space. And with this simple concept, you can order the world according to positive or negative curvature. Here is an example of non-Euclidean geometry. It's a representation of the hyperbolic space by artist Escher, in which each of these fish has the same length considered with the geometry of this space. And in this world, here is how a triangle looks like. It's not a Euclidean triangle, as you can see. The sum of the angles is less than 180 degrees. It's a skinny triangle, so to speak. And if you look at these lines, they tend to separate faster from each other than would be lines that you can draw on your sheet of paper. This is negative curvature, typical. On the contrary, if you do geometry on the surface of a sphere, you see this triangle is fat. The sum of the angles here, these are 3 right angles. So the sum of the angles here is 270 degrees, much larger than the usual 180 degrees, which is characteristic of Euclidean geometry. And if you look at 2 lines, these geodesics, they meet once here, and then they meet a second time at the opposite. In the flat world, if 2 lines cross once, they will never see each other again. But in the world of positive curvature, they can meet again. This is the big difference between positive curvature and negative curvature. This concept is incredibly powerful. And it has also been the source of inspiration for many beautiful geometries. Here is an example. So this is a picture advertising for a beautiful place, which is the Science Museum in Dublin. If you go there through Dublin, go to see the Museum of Hyperbolic Coral Reef, where you find all these things. I don't guarantee that you will find the actress which is represented here, balancing among these beautiful creations, but you will find a lot of these. This is hyperbolic coral reef. It is negative, constant negative curvature knitting. And it resembles kind of coral, but it is made from this geometric property that the curvature should be negative and constant. Just the same as is this figure, the pseudosphere, which was on display at the Fondation Cartier for Contemporary Art during an exhibition of mathematics a few years ago. And the same again as one of these figures, which, by the way, is also displayed here at MSRI at the store, at the stairs above, and floor above. And this one by digital artists Bénard and Palais represents a certain geometric shape which plays a role in the study of some physical system. And again, it has the property that it is constant negative curvature, except for these crests that you see that represent some kind of singularity, in the same way that there is also a kind of singularity here at the basis where it's not exactly so smooth as one could imagine. So here we see three very different pictures, geometric shapes. This one here, and this one here. But for a mathematician, for a geometer, these are three examples of constant negative curvature objects. And we see here how the concept of curvature allows us to classify things and to understand them. Mathematics, said Poincaré, is the art of giving the same name to two different concepts. Let's go back to Bernard Riemann. Riemann, just to say a few more words, unfortunately did not live long. He was, at my age, he was dead, basically. However, he left us concepts that were not only very beautiful and inspiring, but also extremely useful. They were taken up by others, like Gregory Ricci-Courbastro, later, who developed the ideas of Riemann and developed what is known as the Ricci curvature, a variant of the notion of curvature of Riemann, which played a central role both in our program here on optimal transport and in the program of general relativity that were held simultaneously here in MSRI. And later, Einstein discovered that this curvature, here the letter R can stand either for Riemann or for Ricci, was the central actor in his theory of general relativity. So what started to be just a concept inspired by curiosity, by pure mathematics, became a central piece in physics and in our representation of the world. This kind of events is very frequent in the story of mathematics. And one day, this becomes also part of our daily lives, because when you have to make precise measurements and find our way via GPS, in order to get the computations right, you need to incorporate the general relativity effect. So nowadays, it is, implemented in millions and millions of copies. And one should never forget, in a way, when you have your GPS guides you through your, with your car, there is a little bit of Riemann, of Ricci, and of Einstein in it. You can check by opening it. Riemann was also interested in physical phenomena, like this kind of singularities. I showed you some singularities in these negative constant curvature objects. Here are some other types of singularities, like shock waves appearing in fluids, in gas, in air, when you have some supersonic plane, when you throw some ball through some gun or whatever, when you look at the reflection of the light, some singularities spontaneously form, and it is part of the whole field of natural sciences to understand how they are. And Riemann kind of was the first to try to attempt a general theory of these. Riemann, in fact, I told you, was interested in everything, and it's very humbling when you compare the brevity of his life to the list of topics that are named after him nowadays. This makes Riemann a kind of unique, inspiring figure whose impact goes far beyond just mathematics. Actually, once I met a famous rock singer who told me that she goes from time to time on the grave of Riemann to get inspiration, just meditating over the grave and thinking of this great man. This is also something we should, scientists should remember. And from the examples I gave you, we see how much inspiring can be this kind of intellectual constructions of Riemann and the like. I like to go to graves too. And this is me with my hero, Ludwig Boltzmann. This picture was taken in 2006, just 100 years after the tragic suicide of Ludwig Boltzmann in Vienna. You see here the famous formula of the entropy that I will go back to. Just this S is K log W formula is one kind of magic formula, similar to E is mc square of Einstein or other formulas. You could write a whole book on it and so on. Actually, as I like to recall, when I was in this cemetery trying to find my way, knowing that Boltzmann was buried somewhere, but it's such a huge cemetery, it was impossible to find my way. I happened to ask my way to some people that were sitting nearby, and they told me there was no map, nobody to ask for, but maybe they could help, and they asked, "Who are you looking for?" And I answered, "Boltzmann." And the answer was exactly, haha, S is K log W. That was the formula written on the grave of Boltzmann, and that this guy, who happened to be an engineer, had been very much struck by. What did Boltzmann do? Boltzmann also changed the way we perceive the world around us. Maybe even more than general relativity, because this is a phenomenon that we can observe much more frequently. What about the air around us, for instance? We know now, it's a familiar thought, but it was not at all at the time of Boltzmann, that matter is made of very fine particles, atoms, molecules, and so on. And Boltzmann and the others were working on this idea that you can represent the properties of a gas by describing it as a collection of particles that bounce on each other, like the balls in a giant billiard game. And when we think that there is around us something that is still and that there is no wind or whatever, in fact, it's made of billions and billions of particles that hit each other constantly. And the problem was to make sense of this and derive properties from this. This was a kind of revolution which was started by Maxwell and Boltzmann around 1860, 1870. In this revolution, we don't try to describe a gas as a collection of atoms, the atom here, the atom there, etc., as we can see on this slide, but rather we try to take a broader view and to make a statistical distribution, a statistical study of this gas. Like, are there particles which have high velocity, many of them, few of them, etc.? What is the proportion of particles which have low velocity, etc.? And get a kind of curve describing the statistical properties of the gas in the same way as you can get a curve describing the distribution of ages of a population. That percentage of old people, that percentage of young people, that percentage of very old people, etc. The percentage of very, very young, and so on. The same here, that percentage of very fast particles, that percentage of very slow particles, and so on. This was a statistical description of Maxwell and Boltzmann. And it took part in one of the most fascinating stories in science, the slow mastering of chance. Chance, by definition, is things that you cannot predict. You take a coin, you toss it in the air. Will it be heads or tail? Who knows? And started the idea around 1700 that maybe you could, from this randomness, extract some laws that would apply with certainty. Jacques Bernoulli first discusses in this way the law of large numbers. Okay, let's throw the coin in the air. I don't know if it will be head or tails, but I know that if I throw it 1 million times, it will be like about 500,000 times head, 500,000 tails. Kind of. This is the law of large numbers. We use it all the time when we make polls to predict the result of elections and so on. And a few decades after that comes a remarkable event with Abraham de Moivre. De Moivre was a French Huguenot who took exile in England, so he can be claimed both by French and English. Even though he is a good testimony of one of the worst political episodes of France in our history. So de Moivre had this intuition of this Gaussian law that would be a kind of universal profile, statistical profile, describing the fluctuations of the law of large numbers. You know, I toss my coin many, many times. About half of the times it would be heads, half of the times it will be tails, and there will be some mistake. Maybe sometimes it will be much in the favor of tails, sometimes much in the favor of heads. Will the mistake be large or small? I don't know. Sometimes it will be large, sometimes it will be small. But if I look at the statistical distribution of the error, most of the time it will be about 0. A few times it will be very large. Most of the time it will be slow. And it's given by this Gaussian kind of profile to tell me whether it will be large or small. I think this may be the most remarkable theorem, general theorem in all mathematics, that this kind of profile is not particular to coins, but is universal under very general assumptions. You always find it. And another thing that was discovered about the same time as de Moivre was understanding this kind of universal profile is that probability is not just tossing heads and counting. It can also be applied to subtle geometric problems, like in this needle problem by Buffon. Look, you take some floor with some lines, like here. What is the name? How do you call this? Slats, okay, whatever. And here you have this needle such that the length is exactly the distance between two lines. And you throw it once, twice, 3 times, 4 times, million times, etc. Depends how patient you are. And you count how many times will it cross one of the lines. Half of the times, 1/3 of the times, etc. Well, if you do it, the experiment's right. And doing the experiment right means doing it totally randomly. Sometimes you throw it in the air, sometimes you throw it downwards, you throw it very angrily, etc. All kinds of possible ways. And the more randomly you do it, the better it will work. That is the magic. It will in the end be a proportion like about 2/π. About 2/3 of the time it will cross one of the lines. And you see here again, so this is a geometric problem, and pi here, this geometric number, is here to testify of the geometric nature, but it's also governed by probabilities. In 1810, Laplace is the first to give a proof of the intuition of de Moivre that the law of errors really holds. And that if you look at a large number of experiments, they have to be random, they have to be uncorrelated. That is, when you throw the coin in the air, each time you throw it anew, independently of what you did just before, you will have this universal profile like a bell curve, like a Gaussian curve, which is like exponential minus x squared. It will be more and more thin, more and more concentrated to a small error when the number of experiments becomes large. Few decades pass, and Ketele understands that this law of random causes is not just about coins or needles, but also in real life. In real life, and for instance, in statistics about crime in this city or that city, depending on the year, there will be fluctuations, and they tend to be Gaussian. And then, yes, he thinks that is wonderful. Things that we think are just us to decide for, in the end, they are governed by laws of statistics. Galton had the most beautiful words to describe this. He rediscovered the Gaussian law by looking at fluctuations in the height of animals or whatever. I know of scarcely anything so apt to impress the imagination as the wonderful form of cosmic order expressed by the law of frequency of error. The law would have been personified by the Greeks and deified if they had known of it. It reigns with serenity and in complete self-effacement amidst the wildest confusion. The huger the mob and the greater the apparent anarchy, the more perfect is its sway. It is the supreme law of unreason. Whenever a large sample of chaotic elements are taken in hand and marshaled in the order of their magnitude, an unsuspected and most beautiful form of regularity proves to have been latent all along. See here, mathematics, that's the beauty of it. You discover through exploration of the abstract world some laws which apply in the real world. And that is what Boltzmann and Maxwell did with the gas, modeling the gas as something very chaotic with these particles bouncing all around and just looking for a statistical distribution of it, not trying to predict exactly. Boltzmann found some laws which really apply to it. He introduced this quantity S to express the amount of disorder that there is in a gas and how difficult it is to reconstruct the characteristics of one particle in this gas. And Boltzmann gave not only a general formula for it, here W is like the number of possibilities which are allowed by the observations, logarithm is like the size of the number, and k is a constant, but Boltzmann gave a practical formula to compute it in terms of the statistical distribution, so that an engineer, after Boltzmann, can use it and compute the amount of disorder in the gas. This was a very practical progress. And Boltzmann finds the conclusion that entropy always increases and that it is a law that always applies, even though the gas seems random, the amount of disorder in the gas, the difficulty that we have in predicting where one particle will be, spontaneously will increase. Here is how we use this Boltzmann concept to predict something that can occur in an experiment. Take a box, put the gas in half of the box, imagine these are billions and billions of particles, and emptiness, the void, on the other half. And remove the wall at the beginning of the experiment. What will happen? Well, we all know the gas will invade the box. And we like to think that the void kind of aspires, sucks the gas in, as if there is a force. But Boltzmann tells us, yes, this is what happens. But it's not due to a force, it's just due to the laws of statistics. Because entropy will increase, disorder will increase, and it's much more difficult to predict where one particle will be if the particle can wander inside the whole box than if I know that it is in half of the box. The amount of uncertainty per particle is much higher if the gas occupies the whole box. That is the explanation of Boltzmann. Boltzmann used the theory of partial differential equation to substantiate his claim. Look how beautiful. These partial differential equations that for most of you, it's just, you can just look at them in purely, let's say, impressionistic way, are not just pretty formulas, they are very powerful objects and tools created by human mind. This one is the one that Boltzmann was using, the one on top. It's the Boltzmann equation, and it describes the evolution of the statistical distribution of particles in a gas that is isolated. F here is this distribution that I showed you. It may not look very appealing, even for specialists it is considered with a bit of awe, even though there are some partial differential equations, some equations of physics which are even much more ugly at first sight. I remember when I first saw this Boltzmann equation, this was when my advisor was writing it down, and he started to explain me what it was good for, and saying, you know, in a few years when you are quite familiar with the equation, we can start this problem and that problem. And I thought, what? 2-3 years on this equation? Maybe it's time to change and reconsider and do something else of my life. And I would never have predicted what has happened. Starting to work on the equation, I just fell in love with it. And each of these things, when you go inside, you discover it's a whole world. It's connected to a lot of history of science, to lots of natural phenomena, to lots of beautiful connections and deductions and so on. And I spent like at least 10 years studying this equation and very happy about it. So this equation describes the evolution of statistics in a gas. If you don't care about gas but you like stars, you may be interested in the one below. This is the Vlasov equation, which is described to predict how a galaxy will look like after billions and billions of years, starting from a state that we can observe. You can also look at this one if you don't care about stars and you care about things that are very, very small, so tiny. This is the Schrödinger equation, describing the evolution of one atom, for instance, one atom of hydrogen that you will let evolve. Or you can be interested in this or that equations, the fundamental equations of fluid mechanics. This one is the oldest of all equation of Euler. In the 1750s, it was written down. This was the start of another extraordinary adventure, man trying to predict the evolution of a fluid. At the time, it was kind of crazy. You see a fluid in this bottle. How can you hope to put this into mathematical equations? And this is what Euler started to try. Nowadays, it's in our daily world again, in the same way as GPS we use all the time. And here are these equations, this one or the more complicated set that is below. It is used every day to predict the weather forecast or to make special effects in the Hollywood blockbusters and so on. Predicting the evolution of a fluid with this kind of methods, with these equations and computers, it's much more accurate and much cheaper than do it by other methods. And so on. This other equation that I circled here on the left is the equations of reaction diffusion that the British mathematician Alan Turing used to try to understand how patterns would form on the skin of animals, like the stripe on zebras or the spots on the giraffe and so on. A problem involving mathematics and chemistry. So all these equations represent some important phenomenon in our life or in the world. Boltzmann, as I said, used his equation to arrive at a definite conclusion. He used this equation to predict what is the evolution of the statistics of a gas, and he discovered that entropy always goes up. There is this notion of disorder, and it can always increase and increase as time goes. And you can compute what is the amount of entropy that is produced, and there is an ugly formula giving this. And the important is that it's always non-negative, the amount of entropy that is produced, so the entropy always increases. That's the contribution of Boltzmann. It's just the beginning of a story, not the end. First, with this, Boltzmann shows that the gas has to strive for a maximum entropy state. It's natural. If it's always increasing, it will strive to be maximum. What will be a distribution with maximum entropy? Ta-da! The Gaussian again. So here, starting from a problem which is purely physics, we recovered the same Gaussian curve as de Moivre observed looking at the fluctuations of coin tossing, and that Laplace proved was general when you do some random experiment, even though the gas is quite different. This again shows you the connections that you can make in mathematics, and this Gaussian curve, we are back to the same concept, it appears in very, very different contexts, both the gas and the coin tossing. It's very universal. This is only the start of many, many problems. For instance, the late Carlo Cerciniani, one of the specialists of Boltzmann equation, conjectured at some point that you could say more and estimate how much this growth of the entropy is and show that it is, can be estimated, it can be computed in terms of the difference between the entropy, the maximum entropy, and the entropy of the distribution. It was a conjecture, so it's a mathematical statement that looked plausible and was not proven. And this is one of the, let's say, a significant improvement, a significant progress on this question was one of my first research results that I consider significant together with Giuseppe Toscani. For many years, I worked on this problem. How fast does the entropy increase? How fast does the gas become Gaussian, and so on? These are mathematical problems, even though they are very much related to the physics. Boltzmann, as I said, also had a tragic life, not only the same profile as Riemann. He committed suicide in 1906, convinced that his theory could never be checked by observation and that atoms would remain a mystery. However, this conjecture of Cerciniani and the various books that Cerciniani wrote show you that his legacy among mathematicians was extremely strong. And Mark Katz, actually, one of the great probabilists of the 20th century, said that the book of Boltzmann is one of the most important ever written in the history of exact sciences. So not only was it great physics, but also great inspiration for mathematicians. The work of Boltzmann was also key in allowing Einstein and Smoluchowski to explain the Brownian motion at the turn of the 20th century. Also as a manifestation of the atomistic nature of the world and its fluctuating nature. That, by the way, was the experimental observation that Boltzmann thought was impossible. And it was the basis of the work of Jean Perrin a few years later, who used it to convince everybody of the existence of the atoms. And it was also the abstract part of Boltzmann's work with this entropy formula was also rediscovered in a quite different context by Shannon as part of his theory of information. So the Boltzmann formula, we use it every day without knowing in cell phones and whatever, because it is used to compute, to adjust the codes and the channels, the quantity of information that you can get through a channel and so on. And it's also used by engineers to compute the flow of gas in motor of engines and of cars and so on. So in this story of the Boltzmann contribution, we see once again all this multifaceted nature of science from very abstract to very concrete. The entropy actually has been one extremely successful object also in mathematics, including domains which had nothing to do with the theory of gases. I mentioned here on this slide compressible fluid mechanics, information theory, quantitative laws of errors in statistics. The big regularity theorem of John Nash made a crucial use of entropy. The Poincaré conjecture solution by Perelman made crucial use of entropy, etc. Dan Voiculescu, who is, I see here sitting in the audience, used entropy of Boltzmann to make progress in a field that had absolutely nothing to do with the physical world that I described, in a field called von Neumann algebra and sister algebras, von Neumann algebras, and classification of factors. It's also used, it was one of the topics that we discussed during this semester at MSRI, to define what is the heat equation, that is a process of matter diffusing in spaces which is non-smooth. I will not go in this, but it has had a tremendous impact, this entropy. Now, in this world of Boltzmann, in this work of Riemann, we saw practical applications coming many, many years after the theoretical work, sometimes 100 years. But sometimes the applications arrive very quickly after the theoretical work. Such is the case in the work of Leonid Kantorovich, one of the most remarkable mathematical economists of the 20th century, remarkable mathematician in all respects. In his work, he addressed problems that were both very abstract and very practical, be it construction of atomic bomb or taxi fares, and I heard this, that at some point the Moscow taxis, they became much more efficient and fair in computing the fares, and this was the result of the work of Kantorovich's team. He was also a pioneer in the field of numeric approximation and calculators. His main works were treatises in 1939 about mathematical methods of planification and organization of production. Reflect over the title, which is so interesting, mathematical way to organize production in the best way. And so here we see the marriage of abstract and concrete. He improved it for his masterpiece, The Best Uses of Economic Resources, that eventually got him the Nobel Prize in 1975 in economics. So he was the first mathematician to get the Nobel Prize in economics for research in mathematics. Kantorovich is one of the heroes of a novel that I recommend, that I think David will join me in recommending this beautiful novel by Francis Pufford, Red Plenty, which addresses the story of the Soviet industry and productivity, not from the point of view of history of people, but from the point of view of the idea and the people that incarnate or use it. In particular, the ideas of Kantorovich, and how central planification at some point looked like the best thing to do because it would lead in theory to much better results than capitalistic industry, and how it failed because of the interface with humans, so to speak. All this is beautifully explained in the in this work of Francis Pufford. And Kantorovich is one of the heroes of this novel. Kantorovich's life was changed by plywood. Plywood is not something very sexy a priori. You know, it's like this kind of things, right? Where you have several layers of wood that are put together. It's the inventor was the father of the Nobel, who gave his name to the Nobel Prize. And plywood, for some reason, there was this industry in the Soviet world that needed, you know, to show the government that they increased their productivity and whatever. And that wanted to see Kantorovich to discuss with him the best way to increase their productivity in plywood. And they knock at his door, you know. He was quite young, but already the head of his department. And Professor Kantorovich, we have this problem. We make plywood, you know, we take wood from this forest, from that forest. We have this machine that can cut that much of softwood, that much of hardwood. There are so many unknowns. How do we do? Should we put all the hardwood here, the softwood there? Should we do like this and like this? So many unknowns, we don't know how to do with it. And Kantorovich had no clue about how to help these gentlemen. But then he thought about it, thought hard, and understood that it was part of a general abstract problem. Nowadays, it is called linear programming. A problem in which the constraints are given by linear inequalities, like the total amount of wood multiplied by half, of hardwood multiplied by half, plus the total amount of softwood multiplied by 3, etc., cannot be higher than this quantity, which is saturation of the machine, and so on. And linear programming, you have these linear constraints, like you can do in high school, materializing them by lines and the region which is allowed, and you try to optimize, make the best of a certain linear criterion. This was just one example, plywood, of the many, many problems that linear programming developed by Kantorovich could solve. And Kantorovich developed a whole theory using analysis of functions and so on, and understood that as part of his theory, one of the other problems that he could treat was, for instance, the optimal allocation theory, a problem posed by Monge at the end of the 18th century. Imagine you have goods that you produce in some factories, X1, X2, X3, X4, and you want to send them to some places where they will be consumed, say Y3, Y2, Y1, Y4. So you want to minimize the total cost of transportation, otherwise it will pay too much if you want to transport all these goods. Can be any goods, you know, can be can be wood, as in the problem of plywood, can be some metals. In my book, as a good Frenchman, I assume these are croissants that are transported from the bakeries to the cafes because they want to be consumed fresh daily and so on. Can be anything. The problem is, how do you match the production with the consumption? There are many, many ways to do this. And Monge asked this general problem, and Kantorovich understood that his work was giving general methods to solve it. In particular, a beautiful formula which transformed these problems of minimizing the costs, minimizing the sum of the transport costs from start point to final point, into something like maximizing the profit that this intermediate that would make the transport would make if he were to buy the goods from you at the production site and sell them to you again at the consumption site. You see with this the kind of economic interpretation in Kantorovich's work, cost, price, and so on, economy there. You see also how brave this was. Of course, yes, the prices should be well calibrated, that is, the difference of the prices should never be more than the different transport costs from one place to the other. That would be overcharging. You see this economic interpretation and see also how brave this was. He was living in a place and time where the notion of price was very heavily loaded with ideology. And just a theorem like this would have been enough to get you executed, you know. Because even if the theorem says this, it looks like a capitalistic reasoning or whatever. So he had to find all kinds of periphrases, and it was, of course, unthinkable to think of these kind of theorems in public. Since he was so useful and so important for applications, however, Kantorovich managed to stay alive. Nowadays, this theory of Kantorovich and linear programming is used in all kinds of problems. Here are some examples I took from a tutorial. Be it FIFA, the new industries and products mix problem about many types of tie to make per month and so on. I like this one. Be it problems of optimizing advertising in some communication problem, putting some serial, being about portfolio selection, whatever. All these problems, properly formulated, will be part of linear programming. And they will all have the same mathematical formulation. And we see again here this idea that one single mathematical concept can give rise to many, many practical implementations. And also nowadays you have many programs that do it, that solve it automatically for you. Of course, the programs don't work if you don't understand what they are doing, and don't save you the job from understanding what is really programmed and what is the theory of Kantorovich saying. So far for Kantorovich. And at this point you may say that, okay, maybe this was good, but this looked like a very dense talk in which I packed several stories that have nothing in common. Here there was the theory of Ludwig Boltzmann on the right and his notion of disorder and the gas. There was the notion of Riemann and his fat triangles, for instance, that are typical of positive curvature. There was the story of Leonid Kantorovich and his optimization of the cost and economy. And these are three different people in three different cultures for three different types of problems and three different kinds of mathematical theories. And they seem to have nothing in common. However, it was one of the big surprises for me and others working on this to understand that the three theories are very closely connected. And this was at the center of a development which arose kind of by accident and by encounter. Let me explain you why these three are connected, and this was one of the central themes of the research semester that we had here at MSRI about optimal transport. First, it will be the opportunity to recall that science is not done as people may think. Like you just think about a problem, accept the challenge, read, do, think, and get the Nobel Prize or something like this. This is a comic image I extracted from some blog. Instead, it looks more like this. You wonder, accept the challenge, read, then do, then it doesn't work. What the hell is going on? Not going as expected, goes wrong, start again, get amazing result. What the hell is going on? Thinking, no, doesn't make sense, start again, wait, and so on, something funny. This makes sense at last. And then you discovered somebody did it 50 years ago, and you are back to the start, and so on. This is some pattern that is kind of familiar to every researcher. It's not particular to mathematics or physics or whatever. And sometimes after the end of this messy process, you end up with some good, really good idea that most of the time has imposed itself by the kind of accident. In this case, and for me, two of these encounters, random encounters, played a crucial role. One was this Felix Otto, my German collaborator, met in some conference in France, and then whom I came to visit in Santa Barbara in 1999. And the other one is a Berkeley story. This was here in 2004 when I was enjoying the hospitality of the Miller Institute. And this we recognize is the beautiful Berkeley campus, and the not so beautiful Evans Hall. That's one of the first things they told me when I arrived here. The good thing when you're a mathematician is that you don't see the Evans Hall because you are sitting in here. And the other thing I quickly discovered is that the problem with Evans Hall is it's so difficult to meet people because of this vertical organization. And so sometimes you have good conversations, but other times you just don't bump into people as you can do in some other places, and then you wait in your office, waiting for something to be done. So these were great conditions. I mean, with the Miller Institute, I had no administrative duty, no courses, just be there For that, I was paid 3 times my French salary. This was enjoyable. However, where to find the people with and get new subjects? And sometimes, if you believe in destiny or whatever, these occur on you when you don't expect them. And in this case, it was through the action of John Lott. John Lott was here visiting MSRI, so he was just up here from the events hall, and one day came back and arrived, knocked at my door. Hey, I'm John Lott, I'm a geometer. I've read your paper with Felix Otto, entropy, optimal transport. We'll do this, it will be great, apply to geometry. I said, what? Is that really the case? And it was the case, and with John, it was one of the most memorable collaboration in my scientific life. The paper that was out 5 years later as a consequence of this encounter was, I believe, the most quoted paper inside mathematics this year or something. One big hit, kind of. What was in there and what did we develop? This is what I will try to convey to this general audience. This was a new view on curvature, which I will call lazy gas experiment. And you will see in the experiment the 3 different stories that I told you merging together. This did not come on its own. Of course, it was building on previous work, as always. In particular, my work with Felix Otto from around 1999 that I mentioned, and the work of Cordero, McCann, and Schmuckenschläger, which was very important also in the sequel of our work. Robert McCann, by the way, is one of the organizers of this present fall semester here in MSRI, so everything is related. And this lazy gas experiment in the form that we worked and continued to work, that is adopting this unorthodox view as a definition of curvature, was studied in works of mine with John Lott and independently by Theo Sturm. Here it is, the idea. The idea is that we'll see if the world is positively curved by a kind of physics experiment. So that is how you would explain curvature to Boltzmann if he was to come out of the grave that we saw moments ago. Imagine you want to know if the curvature is positive, and what you have at your disposal is gas and measurements on gas. Take a gas with a certain distribution and impose that the gas has another distribution, statistical distribution, after 1 minute, say. At time 0, the gas is like this. At time 1, it should be like that. And the gas will do as you command. But because the gas is lazy, we do this in such a way that it spends the least amount of energy. Energy for a gas is kinetic energy, and the total amount of kinetic energy that is produced by this movement should be minimum. And in between, you measure the disorder of the gas by the formula of Boltzmann. And if that curve of the disorder is a concave curve like this, it is that you live in a positively curved world, if that is always the case. This story is very different from the usual interpretation of curvature that would be something like this, an optical interpretation. If I stand here, look at the star, if the curvature is positive, then the geodesics will get together faster than would do lines in the Euclidean space. And as I don't know it and try to reconstruct the size of the light source, I overestimate the light source. Some kind of mirage, you know? This would be the classical interpretation in terms of light rays. But what I am telling you here in terms of gas is completely different. There is no light here, there's just gas and disorder. And the beautiful thing is that both points of view are equivalent. This is the same mathematical concept of curvature. But to see it in this way gives you, allows you a lot of mathematical manipulations and progress that you did not see with the classical one, and was the start of a number of progress to solve in particular some problems in geometry. See how the 3 elements come together. Because this is curved positively, the geodesics are not just straight, they are curved. And positively curved means that they spread apart before they rejoin. If they spread apart, then the gas following these curves from the geometry is allowed to spread more, because spreading more is more disorder. Remember, in the experiment of the box that you open, the gas was spreading as much as it could to increase the disorder. So in between, the disorder will be higher. And disorder will be low at the beginning, low at the end, but high in the beginning, high in the middle if the gas is lazy. And this concept of lazy gas, of course, will recognize the notion of Kantorovich, of spending the least possible amount of energy to go from one configuration to another. So all the three stories are interwoven in this. And of course, there was no way it could be imagined from the start. It came through these encounters I described to you. This encounter resulted in a 1,000-page book of mine that I wrote, and which I considered as one of the important events in my mathematical life. It just got a prize from the American Mathematical Society as a monograph, which I'm very proud of, but also very happy, because these are really years of my life input in this book. And it is as in life, you know, in science. In life, you meet people by accident and it changes your life. And in science, that's the way too. And you cannot predict who you will encounter. And it's important that there are places like this one where people will meet to discuss on programs, but in the end comes out of this some things that were not predicted. Some place in which people are invited and they can work together and get the best. Institut Henri Poincaré is the same. In Paris, actually, when it was refounded in the 90s, it took as basic principles the same as those which had been edicted here in MSRI, and in particular the fact that there would be no permanent researchers there. Only visitors that come to meet and discover new things. You don't know exactly what it will be, but more often than not, it will turn out to be more interesting than what you had planned in advance. Thank you very much.
We have some time for questions, if you would like. I'll let Cedric choose the questions himself.
Okay, people, don't be shy.
You remarked at the end that the gas expanded. As the numbers came together, as though the entropy.
The microphone is coming. We need the mic.
At one point, you said that entropy always increased, but then in that picture, you seem to have the gas expand and then decrease as though the entropy decreased.
Yes.
So this is, I can guess the explanation, but I'd rather hear yours.
Yes. The explanation is that these are two different experiments. In the Boltzmann experiment, you prepare the gas in some configuration and you let it free. And if you let it free, the gas will always, the entropy will always increase. The gas that is isolated from the rest. But here, this is not the same problem. It's a controlled experiment. The gas will be transported from one state to the other in such a way that the entropy is minimum, that the energy spent is as small as possible. So this does not obey the same laws as what happens when you let a gas free to do whatever he pleases. Precisely a good part of economic activity is to control things and to avoid that the entropy becomes too large. You want to preserve the order. In the same way, in human beings, in any living being, the entropy doesn't increase widely. There are mechanisms to keep the entropy low. These are very different evolutions than in the Boltzmann problem, in which you let the gas free. Here? Here, behind.
Very interesting talk. Is entropy and I think the second law of thermodynamics, is entropy a empirical law based on physics and evidence, or is it a mathematical theorem independent of the physics?
It is both, and it depends on the scope and the kind of system that you are looking. The second law of thermodynamics precisely states this, that if you take an isolated conservative system, it has to be conservative. There has not to be, should not be phenomena by which, for instance, inelasticity or things like this. But you take a system that is conservative and isolated, spontaneously its entropy will increase. And that is a law based on empirical evidence. However, for certain systems, including gas, Boltzmann managed to replace this empirical based observation by a mathematical theorem. That was part of the revolution by Boltzmann. It was a tremendous conceptual change that he was extremely proud of, and rightly so. He could do it only for certain systems, like gas. The second law of thermodynamics applies in a more wide context. Sometimes you can prove it for certain systems. Other times, nobody knows how to prove it. But at least for gas, there is a mathematical proof based on modeling and the equations and this mathematical definition of entropy. The other thing that at the same time Boltzmann did, and which is the other part of the answer of your question, is about the nature of entropy. Entropy was not invented by Boltzmann, or this notion arrived before in the works of Clausius and other people at the time of the start of thermodynamics. But Boltzmann gave it a mathematical interpretation based on combinatorics. He gave a mathematical definition. Before that, it was just an empirical definition, something that you can compute and a quantity which always increases, and such that you can compute its variations, but not the quantity itself. Boltzmann changed this into a mathematical formula, and this was extremely useful. And we saw this formula appearing in many places, including information theory. Even when the second law of thermodynamics doesn't apply, the fact that there is an interpretation of the entropy is most important. There.
On this new way to conceive these positive curvatures, that gets me back to the Riemann conjecture about odd and even numbers balancing out to infinity. I think I found a way how to do it.
Mm-hmm.
If you'd be interested, and I'd talk to you about it.
Okay.
And also,
let's discuss
the
this
Fermat
after.
thing. Did you think he had a new way of doing things and took it to the grave with him on Fermat's last theorem?
Riemann?
You think that's possible?
Well, who knows? It's.
Because I got a pattern to show you.
Okay, let's discuss this afterwards with pleasure. Here.
You discussed the connection to positive curvature in terms of the behavior of geodesics, and one way to look at light geodesics is in terms of stationary phases in a path integral. Is there a connection between the lazy gas way of looking at things and the path integral way of looking at geodesics?
There are various ways to reinterpret this lazy gas experiment, and in particular in terms of optics, maybe the most important way is in terms of the evolution of the phase as described by what is called Hamilton-Jacobi equation. And this kind of picture here can also be understood, and it's important that it be understood in some pictures. It's important to understand it this way, in terms of the evolution of an optic phase as described in this Hamilton-Jacobi equation. And in this interpretation, the unknown which appears there is the same as the price in the Kantorovich theory. So it's like we're looking at the evolution of prices all along the process. That's not exactly answering your question, but at least it's still another way to interpret it in terms of phase. Here.
I hope this is not the same question, but an extension. It seems that you lead us to the place where you would say that general relativity would have there's some kind of entropy implied in the equations of general relativity.
It would require long debate, but entropy, as I described here, is related to matter. When we think of general relativity, it's into matter and statistical matter. When we think of general relativity, we think of space-time first. In space-time in itself, there is no issue of matter. However, if you want to understand gravity within general relativity, of course, we have to put some matter and has to be described by some equation. Often it is described by Vlasov equation, like it was one of the equations that I showed that is used to describe galaxies and so on. And then you have equations called Einstein-Vlasov models and so on, with the coupling of geometry and matter. In this context, one can study what happens of entropy and so on. But the source of the evolution of the entropy will not be the general relativity in itself. It will be the process, irreversible processes that are affecting the matter. Yes, that is how I would present things. Now, there is a quite different thing called the entropy of black holes, which has been the subject of many developments recently. But it is somehow another interpretation than the entropy, which, okay, it relies on similar basic concept in the end, but it takes some twist to go through. I would not think so, but maybe I'm wrong. It seems to be a completely different problem here, but you never know. There is here.
I think we need to wrap up soon, but perhaps there's a question there, but perhaps you could say something about what comes next. What isn't done yet in this field? What would you hope to accomplish at the next program?
Yes. It's easy to describe about the start of a program because often the basic idea is so simple. And then when you explore everything that is simple, the problems that are left open sometimes are so complicated to explain. To try to say things in an understandable language. First, you see here, this is a new way to conceive positive curvature. It's a way that is extremely general, which doesn't require what people call smoothness. It can be defined even in a space in which there are lots of singularities in geodesics and so on, a bit like the singularities I showed when I explained about the work of Riemann and these wave shocks. When we have a wave shock, you have a discontinuity of something is not smooth, some tangent doesn't exist, and it's a whole thing to see how much you can do geometry in this way. A lot of the smooth geometry has been adapted to the non-smooth geometry in this concept of curvature. A lot, and also recently we were discussing again this morning in the working seminar of recent work done in this respect, which goes nearly as far as we hoped to. So let's say it's kind of exploring this non-smooth geometric picture. There are some islands of that remain that are still obscure. but quite a bit has been explored. A thing that looks a bit more anecdotal, but which is really dear to me and that I really would like to do in this field, is understand with these concepts of entropy and Riemann, understand isoperimetric inequalities. Isoperimetric inequalities are isoperimetric principle of the principle which relate the surface of a body and the content, and which say that, for instance, if you want to minimize the surface of a body for a given volume, it has to be a sphere, a bubble. That's the reason why when you make soap bubbles, they have the form of a sphere. This is the isoperimetry problem. And this isoperimetry problem is one of the fundamental problems in geometry. It goes back thousands of years ago. It can also be set in non-Euclidean geometry. You know about the surface. You want to minimize the surface for a given volume. And there are theories for this. But the theories for this, they are formulated in very sophisticated terms. I would love to get a formulation of these theories in terms of entropy and explain to Boltzmann, here is how to understand the isoperimetry. This is still not done. This maybe of all the problems in this field, this is the more dear to me.
Maybe if you still want to ask a question, I'll declare that will be the last one.
After that general question, I was going back to something specific. You mentioned information theory earlier, but you didn't do any connections with information theory and just other than, I guess you mentioned Shannon, but
yes.
I didn't hear anything else.
Yes, what is the basic principles of information theory, in particular communication theory, which is how it was started by Shannon and his collaborator. And the basic ideas is you are interested in the transmission of message. Message is made of signals, and you can be interested in the statistical properties of that signal, like alphabet. When we speak, words have a meaning, but words will not be equally distributed. Very often we'll have words that don't have much meaning, like the or e, and sometimes words with a lot of precise meaning, like computer or light, and so on. And if you're interested in transmission, this is important. Maybe if I take out all the and so on in the text, it will still be understandable. But if I take out computer from my text, it will not be understandable. And you can ask the question, how can you compress? I have to transmit this long message to this other message. How fast can I transmit it? By coding it first, then transmitting the code, then uncoding, and so on, decoding. These were the kind of questions that Shannon was interested in. Obviously, it's a very general question whenever you have communication nowadays, with computers, with cell phones, or whatever. One of the keys in the approach of Shannon was to try to forget as much as possible the idea of meaning. Let's decide, thought Shannon, that language is just a probability distribution over words, for instance, or could be letters, but let's put ourselves at the level of words. Some words are rare, some words are frequent, and thus I have my probability distribution. And then Shannon thought, a rare word conveys a lot of meaning, so I will attribute a lot of value to it. And the value of the word, the importance, should be a function of the inverse of its frequency. If it's very rare, it will be very precious. And he also reasoned that there should be some quantity of information that the words carry. And this information, if I receive it from two different channels that are independent, it should just be the sum of the informations. Information from this and from that will add together, and this would be the start of calculus on this information. However, we know from probability theory that if you have two independent signals, the probabilities are multiplied, like the probability that, I don't know, that this computer breaks or that your car breaks. A priori, I just have to multiply the two events, they don't influence each other. in the probabilities are multiplied, but I want the informations to be added. Then he said, what is a mathematical transformation that transforms multiplication into addition? It's a logarithm. And there we were with the idea that the infinitesimal, the unit of information of a given signal, a given word, should be like the logarithm of the inverse of the frequency of that word. And then, because that bit of information, that amount of information, is transmitted only as often as the word itself appears, I have to weight this logarithm by the frequency itself. So it was like the sum of the frequencies multiplied by the logarithm of the inverse of the frequencies. And there he was back with the Boltzmann formula. And now, this he found as for instance, he identified this entropy as the best way, the minimal length of encoding that you can achieve. If your entropy is very, very low, then you can make an extremely efficient code. If your entropy is very high, the code will not be allowed to compress so much the information. It seems to be very different from the Boltzmann, but not so much. It's about, remember, Boltzmann is about the disorder, but it can also be interpreted as how much information can I have about a particle in the gas? There are various definitions of entropy. There is the Boltzmann entropy, which coincides with the Shannon. There is the Kolmogorov entropy. There is the Sinai entropy. They all have in common that it is about the amount of information that you can get on an unknown system in one way or the other. And here we see, as in this problem of extracting the information from a language and seeing the information in a particle, there is a parallel, again, in the mathematical world. That's the connection between the Boltzmann entropy and the Shannon entropy, and the reason why they are formally equal to each other. Here we are.
Well, I think it's time to call a close. We've seen some of the vast richness of mathematics and its interaction with physics from a truly master expositor. Thank you very much for this.
Thank you, everybody.